Okay, so our purpose is to continue our discussion of electric fields. And I want to review and extend a little bit of what we did yesterday and then do some actual computations so you can see how it's going to go. Here are the salient points from yesterday. Electric field is going to be emitted by positive charge and captured by negative charge. So the picture that we can draw is that the electric field lines are going to come out of positive charges and they're going to go into negative charges. And in particular, we say that the electric field concept was invented so that we could write the simple equation force equals charge times field that is analogous to force of gravity equals mass times g. Now I say analogous to because the units here are going to be different. If you just work out the units on force, of course, will be newtons, and the units on charge are going to be coulombs, so the units on the field have got to be newtons per coulomb. Exactly.
So, Mr. King,
Yes, sir.
would you like us to think of the F equals QE as the base formula, whereas simple CAD is
Good. Very good. Yes, that's exactly right. And if I were to be specific and precise about it, what I would say is that the electric field is technically going to be, this is the practical equation that we'll use here, but the official equation expresses this in terms of a limit, like this. And the reason they express it in terms of a limit is that when I actually place that charge into a field, so here comes my Q right here, place that charge itself is going to emit field that will distort the field around it. And so to remove the distortion of that field, technically I want to let Q go to 0. The actual practical effects of that are ignored in most computations. Yeah?
Another question, so newtons can never equal negatives, right?
Oh, can you have negative force come out of this? Yeah, actually. That's right. So if I take this positive Q that I've got right here, or this Q, and I place it over in this field right here, then the force will change direction. So remember that one of our important points is that charges are going to fall down the field lines in all cases, which means that positive charges are going to fall down away from other positive charges, but they're going to fall up towards negative charges in that way. Or a better way to put it is that negative charges fall up towards positive charges. That's what I mean to say. Good. So there's that. I want to talk a little bit about the visualization in field lines because the field lines kind of look like vectors, but they're not. And so I want to be really clear about the field line part of it, the visualization part. And then our focus mainly today is going to be on the algebra of the field. One of the skills that you want to be able to have is to sketch what a field should look like around with a set of charges. And yesterday we laid out the following rules. We said that the number of field lines coming out of a charge is going to be proportional to that charge. Amanda, you got a question? Mm-hmm. Okay. The number of field lines is proportional to the charge. So, if I have plus Q right here, and I choose a certain number of field lines to be coming out of that Q right there, hopefully I chose an even number, then if I have half of that charge plus 1/2 of Q, then I would use half as many field lines coming out of that charge. And the choice for the baseline number of field lines is really up to you. The more field lines that you draw, generally speaking, the more accurate your drawings might be, and the fewer that you draw, the sooner you get to go home. Let me show you some pretty drawings of field lines here. There's some pretty drawings of field lines. Now, I want you to notice a couple of things. One of those things that I want you to notice is that we actually got two things going on. Everybody see the little tiny arrows? The little tiny arrows right there are not the field lines. They're tangent to the field lines at those points. Those are actual electric field vectors. So you can think of the electric field as a mathematical object that we haven't encountered before, a field. And a field in math is a function that assigns a vector to every single point of space. Just kind of a weird idea. So picture this, the entire space filled with vectors. And there's your electric field. These lines, on the other hand, are legit field lines. And you can see that one of the things important about those field lines is that they actually bend, like so. And the other thing that's important is that the field lines are going to go from a positive charge over to a negative charge. And the next thing that's important about the field lines is their density. You'll notice that if I draw a square around the field here and draw the same size square around the field here, that there are more field lines, the field is denser here than it is here. The density of the field lines is proportional to the strength of the field. So, let's just get these facts here on the table. Number of field lines is proportional to Q. The density of the field lines is proportional to the field. Yes, sir?
On the picture, is there a reason that they have like big gaps between?
Yeah, it was computer drawn. I think the computer was not fully uniform.
So, do field lines represent the electrical force?
That's a great question. Do field lines represent the electrical force? Let me just continue to develop some things about the field, and I'll address that question. So then the next thing to understand is that the field lines are not vectors. For example, a curve. They have no fixed length, meaning that once I start drawing a field line here, it actually continues out until, maybe it'll curve away from this positive charge right here, right? It'll continue out until it gets captured by a negative charge somewhere. So the field lines always start on a positive charge and always end on a negative charge. There are no free field lines. There are no field lines that just come from nowhere and go to nowhere. Now sometimes that positive or negative charge might be off the page. So a lot of times you'll see me draw a field and there'll be no obvious negative charge over here. That doesn't mean there isn't one, it just means that I have drawn it. That charge is, practically speaking, out of infinity. Are not vectors, no fixed length, and they always start on a positive charge and terminate or end on color negative charge. So the field lines are not vectors in these ways, but the tangents to those field lines are vectors, and they are the field. So that's the answer to your question. The field lines themselves are not the field itself, but instead what it represents is the trajectory of a bunch of different tangents to those field lines that are the field vectors themselves. So if I have a field line, like so, then I can draw myself a tangent vector, and that tangent vector is going to point in the direction of the field. And if I'm doing it sort of proportionally, then it will actually have the right length of the field. So this means that if I place a positive charge, this is the key point to remember. if I place a positive charge anywhere on a field line, that positive charge is going to experience a force in the direction of that field line. In other words, positive charges fall down field lines. And if I place a negative charge anywhere on a field line, then that negative charge is going to experience a force opposite to the direction of that field line. In other words, negative charges fall up. Does that make sense? Okay. The picture that I'm trying to draw is a picture that is very similar to gravity, with the one major difference being that we have two kinds or two flavors of charge instead of just one. So we have things that can fall down and things that can fall up. And the second major difference being that for gravity, we're used to the idea, at least near Earth, of gravity being uniform everywhere. All objects accelerate at 9.8 meters per second squared in the surface of the Earth, except under the conditions of air resistance. Whereas for electrical charges, because the electrical force is so much stronger, you get a large amount of variation in the electrical force, depending upon how close or how far away you are to those charges. And so the basic experience in everyday life that you want to think about is the experience of static electricity. If you charge yourself up by walking across the floor and you get near your cat, and your cat's a long-haired cat, then your cat is not going to notice until you come within a couple centimeters and then the hair starts standing up, and then you come within a couple of millimeters and bzzz, you manage to transfer electrons from yourself to the cat. Well, that's because the electrical field is increasing as you get closer and closer to the cat, so that at some point the electrons just fall upwards toward the cat, and that's it. Does that make sense in terms of the picture? Okay. Now, let's talk about what I've drawn fields for positive charges in isolation, for negative charges in isolation. Let's put charges near each other and see what the field does. And then let's put a large number of charges sort of continuously near each other. So we're going to do two things. First of all, we're going to put a positive charge near a negative charge. And we're going to arrange it so that we have twice as much positive as we do negative for this example. How would we sketch the field? Now, our sketches are going to be really crude, so please understand that these diagrams are going to be approximations, and with my bad art, they're not even going to be great approximations. But remember our basic rules. Because I've got plus 2q and because I've got minus q here, I'm going to use twice as many field lines coming out of plus 2q. And because this one is positive, field lines are going to come out of the positive and go into the negative. And we're going to make sure that fully half of the field lines that come out of here are captured here, and the other half are going to go out to be captured by other negative charges. So let's pick a number for minus q. How about 6? Does that work? So we're going to have our field lines near the minus q are going to look like this. Basically symmetrically arranged, like so. Okay? And we're going to have, therefore, how many field lines coming out of plus 2q? 12. Yep. And so here they go, also symmetrically arranged. So we're going to have to do something like this. So this is our preliminary start for how this is supposed to go. Let's see if I can get 12 equally spaced field lines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, like a clock. Okay. Now, we're going to have to continue these field lines toward the negative charge. This field line is easy. It's going to go straight across. Boom, like that. These other field lines, the ones especially that are near the minus q, are now going to curve towards the minus q, like that. So we're going to have a field that does this, just like so. That took care of 5 of our field lines. Probably this one coming straight into the minus Q over on the right, probably that's going to have to come from some positive charge off the page here. So we'll draw that part of the field like this, and we're going to draw the rest of our field as being basically bent. Let's see here. That one's not going to get captured, so we'll have him sort of kind of come out and kind of bend like so, and then a little bit like so, and then like so, and straight out, and a little bit of bending, and like that. Okay? So we have twice as many field lines out of plus 2Q. They're going to bend in the direction of the minus charge right there, which makes sense. And we're going to have half of these get captured by the minus Q. Why half? Because the minus Q is half the charge. So that's our basic sketch and the principles that make it happen. Does that make sense? Yeah.
So the field lines on the negative charge, why do they go in?
Because the negative charge is negative. Yeah. So the field comes out of positive charges and goes into negative charges. And it's funny because I gave you kind of a non-answer in some ways, right? Just because. But actually, that is like a fundamental thing about the universe that we would observe rather than explain. Electric field behaves that way with 2 different flavors of charge just because.
Wait, did you say half of those are supposed to be?
Well, we can't really make this guy
Yeah.
yeah. So it's not exactly 1/2. Remember that these field lines are representative, right?
Yeah.
So if I were to draw this one with 2,000 field lines and that one with 4,000, then we'd see half or 1999 or whatever. Yeah. So just approximate. What if I were to place 2 positive charges near each other? So let's do like plus 2Q and plus Q. What changes now? Well, what changes is that the field lines over here can come out instead of in. I'll try to do that evenly spaced if I can. And again, we do the 12 over here. Okay. And now, as these field lines approach each other, here's an important point. The field lines cannot cross each other. They will never cross. Why not? Because if they were to cross, then at that point there would be 2 different tangents. There would be 2 different values of the electric field. That's not possible, because the field is a function for every point. There's a vector right at that point at which we have the electric field. So our electric field lines, when they encounter one another, so to speak, they're actually going to combine or superimpose to create a field that is in the direction of the 2 of them put together or added together. And that's the principle of superposition. Fields add. So here we go. When we get these 2 field lines near each other, they're actually going to bend out like this and like this, so that no field lines end up getting captured here. This guy is going to bend one way or bend the other, maybe like that, something like so, so that the field lines are never going to cross, and they're also going to be bent out away from each other, like so. So my field ends up looking something like this. Notice that the greatest amount of bending and distortion happens in between the 2 charges, whereas a much lower amount of distortion happens out here at the edges. Okay? And no field lines get captured here. The negative charges that are capturing these field lines are off the page. They're out there somewhere. Now here's the cool part. I can't do this because I don't have the capability on the smartphone. But imagine for just a moment that I take this whole thing and I zoom out 10 times. And if I were to zoom out 10 times, take a look at what happens once we take all of this field and kind of look at it in a large scale. So here's my +2q, and here's my +1q, and now I look at the field coming out of it, blah, blah, blah. Here's what I see coming out of it. All that distortion disappears at a large enough scale, and what I end up seeing is how many field lines? 12 plus 6 is 18 field lines. Okay, that's proportional to 3 charges. So that at a large distance, a 2 and a 1 together look just like a +3 charge. So then we discover that charges add. And actually, if you were to go back to our previous thing, that's also true with the negative charges. 2 plus -1 puts out just as many field lines as +1. Now, if you think about this in terms of atoms, now the properties of atoms start to make sense. Take a helium atom. +2 charges for the protons, -2 charges for the electrons. If you are near the helium atom, you will experience some of this like field distortion. But if you zoom out away from the helium atom, even at a distance of twice its radius, then the effective charge on that helium atom is going to be 0. And so the helium atom will be neutral, which is basically how you treated it in chemistry, right? But then you have this weird thing where if the atoms get close to each other, they experience like intermolecular forces. What's up with that? Well, that's all of that field that's happening in between, and that field is going to be pronounced when there is a charge separation or a dipole. Remember that? Dipole is just Greek for 2 poles, plus and minus, right? So you've got a dipole, and as a result, at a large distance, no charge. And at a small distance, you now see the effect of having the charges separated by a little bit, and that's electric field. Well, I've just sort of dumped a whole bunch of concepts on you. I'll let you kind of chew on those, and let's talk about the algebra now of the field, and how does this work out. We want to consider algebraically the field as a result of 2 different things. First thing that we want to consider is the field as a result of a single point charge. That's what we've been drawing up here. We want to compute it now. So our first goal is I put a charge here, and I want to know what's the value of the field at point P. And I want to know the magnitude and direction of that field, thinking of it as a vector quantity. We can already tell what the direction is going to be. It's going to be straight out. Okay. Now, the second thing that we want to consider, once we've done that, is the field as a result of a long, thin sheet of charge. Now, that may seem kind of arbitrary, why that shape instead of some other shape. But the reason that we're doing that is that the basic way in which we store charges is with a device called a capacitor. And that capacitor, at least in the simple version of it, is going to be 2 plates of metal. And one of them is going to have positive charge stored on it, and the other is going to have matching negative charge stored on it, and there it is. So what we'd like to do is to be able to calculate field for it, and one of the reasons is that it's really simple to do. So our picture here is what happens if I have a long, thin sheet of charge like that. Okay. All right, let's tackle the point charge. We actually have the math to do that because we already know 2 things. We know, first of all, that the force as a result of a point charge is given by Coulomb's law. And that's going to be K times Q1 times Q2 over R squared. And what this means is that if I have my Q1 right here that is producing the field, and I now take another Q2 and I put it near that field or in that field, it's going to experience a force, and I already know how much force, K2Q over R squared. But also, I know that the electric force, no matter what type of charge or distribution we're talking about, is equal to charge times field. So that if I am looking at the force on Q2 exerted by Q1, then that is going to be equal to, let's make this specific so we can keep our heads straight. The force exerted by Q1 on Q2 is equal to the charge on Q2 times the field exerted by Q1. F equals QE. Well, now it's just a matter of putting these two equations together and doing a little bit of algebra. If we take, you know what, let's group all this and kill it, because we're going to need a whole nother page for it. There. Okay, we'll come back to that. So we lost our Q1. There. So let's put those two together, set them equal to each other. Cancel, cancel. And behold, the field that is exerted by Q1 is equal to KQ1 over R squared in terms of magnitude. And it's, well, it's not an accident. We just showed that it comes right out of Coulomb's law. What about the direction of that field? The direction of the field is going to depend upon the charge on Q1. If Q1 is positive, then the direction is going to be straight out. So if this is my positive charge right here, and let's say this is my point P right there, then the direction of the field generated is going to be straight out from the positive charge. Yes, ma'am?
Why isn't the field line coming like just straight from the
Great question. Remember that the field lines are not vectors. We're actually now drawing the electric field vector itself, which is slightly different. That's just a tangent to the field line. If I wanted to get the whole field line, what I would have to do is to get tangents all along here and connect the dots. And I'm not doing that. I'm just finding the value of the field at a single point. So really good question. The answer is different objects. If, on the other hand, my charge is negative, then the direction for that field is going to be straight in. So if this is my point P, then my field from negative charge is going to be straight in towards that negative charge. Okay. Well, let's take a minute to actually work problems. We should pause for calisthenics. We're losing people. Yes, ma'am.
Like in the book, they use like a capital Q and then a lowercase q. Like,
Yep.
I think they use a lowercase q for like a test
The
charge.
test charge, right.
Like, does that like
The designation is just, they're just provided rules.
Okay.
So I'm using 1 and 2 subscripts to distinguish my charges. They're using uppercase, lowercase to distinguish. You say potato, I say potato. Okay, so let's actually do an example. Let's find the field. Back up. Let's do a setup here. A 3 microcoulomb charge plus 3 microcoulomb charge is at the origin. Find the field at 2, 0 centimeters. So notice that we have a charge in a particular location, and we're now going to find the field at a different location. Let's go ahead and draw this so we know what we're talking about. We're looking at plus 3 right here, microcoulombs. Now we're going to go over here to 0.2, 0 centimeters. So we're going to use our, let's call it Coulomb's field law, KQ over R squared, to generate the magnitude, and then we're going to use our straight out, straight in idea to generate the direction. So the field is going to have a magnitude of K times Q over R squared. Part of the tricky thing is to pay attention to the units. So micro is 10 to the -6, and centa is 10 to the -2. So I've got to watch out for both of those. Times 3 times 10 to the -6 coulombs over 2 times 10 to the -2 meters, just like that, and that's squared. Let's do our mantisses and exponents separately. So we have 9 times 3 is 27 divided by 2 squared is 27 divided by 4, which is going to be just shy of 7, 6.75, times 10 to the, let's see here, 9, 10 to the 9th, 10 to the -6, add the exponents to get 10 to the 3rd, divided by 10 to the -4th, subtract the exponents, careful with that negative. No. So 3 minus -5.
Wait, it's on the bottom, so it's...
Yeah, that's right. So 10 to the 3rd minus -4 is 10 to the 7th. Dang, that's a lot of, what's? Meters squared cancel, one factor of coulombs cancels, leaving the other behind. So we get 6.5 times 10 to the 7th newtons per coulomb. That is a seriously strong electric field. That's actually strong enough in air. The field value that causes arcing is, I forget the precise value, but it's tens of thousands of newtons per coulomb. So this will go well beyond that. This charge right here is going to be sufficient to cause like weld or something. Okay. All right. Let's change our. Oh, we didn't find the direction. We found the magnitude, but our field is a vector quantity. It has a direction. So we're going to use our straight in, straight out idea. Is the field going to go straight out or straight in? Out. Positive charge. Boom. And so therefore our field as a vector can be written as 6.75, 0 times 10 to the 7th newtons per coulomb. Notice that it's often convenient to write the exponent on the outside.
Can you do it on everyone if it's going off to some crazy direction for like the top right?
Yeah, in fact, I'm about to switch up this problem here. So let's do the same thing at a different point. Find the field, find the magnitude and direction. Or let's just say find the field at the point 3, -1 centimeters. So our point 3, -1 is now down over here. We're going to do the same idea. We're going to say that field, E is equal to KQ over R squared. And And we're going to use the same Q that we did before, times 10 to the 9th, Newton meter squared per coulomb squared, times 3 times 6 coulombs over. Now, for the r squared here, observe that the r is the distance, and therefore I have to use Pythagorean theorem. Fortunately, that's going to give me 3 squared plus negative 1 squared centimeters squared, which I'm going to represent as 3 squared plus 1 squared times 10 to the minus 4 meters squared. So think about that for just a second. We do component squared plus component squared gives me r squared. And so that's going to give me 27 again, but now we have divided by 10. So that's going to be 2.7 times 10 to the 7th newtons per coulomb. That's our magnitude. What about components? Well, I can do this in one of two ways. One is I can find a direction angle and express this in polar form. So if I find the direction angle, then I would say theta is equal to the inverse tangent of y over x. And the y and the x are specified by the location. And so that would give me inverse tangent of negative 1/3, and I don't know what angle that is, but it's going to be some negative angle that is going to be somewhere about 15 degrees. Let's see. Inverse tangent, 18 degrees. Negative 18 degrees. So that's one way to handle that, is to use these to use the x and y to find the direction. And that's a familiar computation for you guys. A second way to handle it, the one that I kind of like, is if I want this in rectangular form, then I can resort to a cheap trick. And that is that the cosine of this angle is equal to the x component divided by the radius. So the cosine is automatically 3 over the distance here, which is root 10. And the sine is going to be the y component divided by the radius, or negative 1 over root 10. So if I wanted to, I could say that my magnitude here times the vector 3 over root 10, negative 1 over root 10, is automatically my vector in rectangular form. And these quantities right here are the cosine of the angle and the sine of the angle, and I never had to compute the angle. That's the advantage of doing it in this way, is that you can work strictly with your rectangular components and never have to worry about the angle. And you can distribute here to get numbers if you want. So we've got a couple of different ways that we can express our final answer. We can say the field is either 2.7 at an angle of negative 18 times 10 to the 7th newtons per coulomb, or we can say it is 2.7 times our roll direction vector here, times 10 to the 7th newtons per coulomb. Okay. If we're adding field, this is probably the easiest way to go on the bottom. All right. So, I promised you long thin line of charge. That's going to be important. We're going to do this conceptually. But I want you to imagine, oops, wrong color. Let's do this for a positive charge. Let's imagine that we take a long, thin line of charge, and for the sake of it, let's assume that our charge is evenly distributed. The easiest way to do that is to put our charge on a piece of metal. And because charges can freely flow within a metal, they're going to all distribute themselves so that they're essentially evenly distributed or evenly spaced. Because in that way, without any charge clumps, then you minimize the total amount of energy in there. Okay? Now what happens with our field? Imagine each little piece of charge here exerting field coming out from itself, right? And then when those field lines encounter the other field from the other pieces of charge, they're all going to superimpose or add together. When they add together, any field lines that are in opposite directions are going to cancel out. And any field lines that are in the same direction are going to enhance each other. They're going to add together and work down. And to do this properly requires a little bit of calculating, but you can imagine, it's not too hard to imagine, that except right at the very edges, what's going to happen is that all of the field that is coming straight out is going to be enhanced, and any other field going off in any other direction is going to get canceled out. And so the net result is that you're going to get field coming straight out on both sides. And if this line of charge is infinite, then it will just be straight out. Around the edges, you'll see a little bit of bending, but only at the very edges. Okay. Now, if we take and put a negative charge, a negative thin line charge, the thin line got too thick, like so, then that negative charge is going to capture in much the same way that this emits. It's going to be exactly symmetric, so that what you end up with is going to be field that goes straight across, except again at the edges where it kind of curves like that. So you're going to have some stuff that does this. But let's focus just on this part right here. Of course, you've got field lines from the other side, in case you're wondering. But we care about what's going on right here in the center. Remember our graphical principle, which is that the density of the field lines tells you how strong the field is. So what I want you to observe is that the way that I've drawn this, and in fact the way it has to be since the charge is evenly distributed, is that these field lines are going to be equally dense all the way down. And so what we find here is that between the two plates, the field is constant. And it is constant because all those KQQs over R squared add up to a constant field. And you'll just have to trust me that the calculus works out on that. Between the plates, E is constant. Now what does that mean for our purposes? What that means for our purposes is that this is as close as we can get to something like the constant gravitational attraction of Earth near the surface of the Earth. Just as weight equals mg, so also between the plates, force will be equal to QE, and E will be a constant number instead of some function of distance. That means that inside here, charges that are released are going to experience a constant acceleration. This way if they're positive, to the right if they're positive, and to the left if they're negative. So the only difference really between these two plates in gravity on Earth is that we can have negative charges that fall upwards. So you want to think of the positive side as being the upside and the negative side as the downside. So we just have to turn our heads to kind of see it. So now if I release the positive charge, it's simply going to fall down. Does everybody see that conceptually? I understand that you're not in a position to do the calculus work. Don't worry about that. Since we have like a minute, I want to show you another charge distribution that's really cool. Let's suppose that I take a hollow sphere and And my hollow sphere, and that's not too hard to make actually. I can make a metal sphere that's hollow, right? And I can now put charge on that hollow sphere. And when I do, that charge is going to distribute itself so that it's evenly distributed all the way around. So what can I say about the field? When you do the calculus, it's really kind of cool. On the outside, the field looks just as if it were all of the charge distributed at the center. So you get KQQ over R squared for your field on the outside. On the inside, something magic happens, something mathematical happens. And that is that when you add up all the contributions from all these positive charges, you get 0 everywhere inside the sphere. No field. What monofield? Because the field cancels out. Now here's a great way to see this. Some serious calculus goes into this. If I take and draw an imaginary lasso around, imaginary three-dimensional lasso, around my hollow sphere, if I draw it on the outside, then what I get is that the total amount of field lines coming through my imaginary lasso is proportional to the charge that is enclosed on the inside. So that if I draw it on the outside, I get KQQ over R squared for my field. If I draw it on the inside, there's no charge on the inside, there's no field. That's pretty cool. I'll see you tomorrow.